Okay, so there's a key hint given here. A couple of key hints. So it says, for one thing, it blatantly says use the unit directional derivative. Now, that does not necessarily mean that the unit directional derivative is our answer. They just want us to compute it with the unit directional derivative. Okay, fine. Then it says rate of change of the depth per unit distance traveled. Well, if you think about it, what that means is if you're looking for the rate of change of this depth function, we don't have a name for this. I'm going to call it H. So dH ds, right? So that says, so rate of change, per unit distance traveled means that we're looking for, the slope, right, of the graph. So what this is the unit directional derivative. So we're going to use the unit directional derivative to compute the unit directional derivative. So that's why I say this was kind of a hint, that the answer is the unit directional derivative. And then there's one other little tip off here, sort of a hint, and that is it does say here in the direction of this vector. So it doesn't say with velocity this vector 12, 5, right? So specifically by saying the direction of the vector, we're saying the magnitude of this vector doesn't matter. I'm just using 12, 5 as a convenient tool for talking about what direction do I want to indicate. Okay, so we want to compute the unit directional derivative. Let's call this vector here v, and keep in mind that has a magnitude little v, scalar v, and then a unit vector direction u, and I'm interested in computing this unit directional derivative at the point 1, 3. Okay, good so far?
Yeah.
Okay. So now we have a couple of choices on how to compute this. I could deal with this directly. The trouble is that this u vector, it's not the worst in the world, but I can write down what that unit vector is. It's a unitized.
12 over 13.
Yeah, the magnitude's 13. That's right. So the vector turns into, as you say, 12 over 13, 5 over 13. And so we're going to be playing with fractions if we go through it this way. So out of laziness, I'm instead going to compute the dv h13 and then divide by the speed. Right? The idea being that, per this observation here, I could rewrite as u is equal to v over v. And so that vector comes, you see where that came from. It comes out of that fact. Does that make sense?
Yeah.
Okay. Right. So conveniently, this expression is going to be easy to compute because the vector is an integer, or has integer components. Okay. All right. So now we're going to let's not forget to say 1 over v. Of course, v is 13, as you noted. So 1 over 13, and then I have a derivative with respect to t, evaluated at t equals 0, and then I have h of a plus tv. Does that make sense?
Yeah.
And from here it's all plug and chug. In other words, you combine this into a single vector that gives you your x and your y. Once you know your x and your y, then let's see, let me clean up my mess a little bit. H is that function. Yeah, take the t derivative, plug in t equals 0. Don't forget to divide by 13 at the end.
Okay.
So it's all algebra from there.
All right, perfect.
Cool. All right, let me pause the recording.